Okay, so here it is. Okay, so I start with a similar picture as in last Monday. So this, again, the keywords I said last Monday. So for today, there's less things that I can say about the tropical side of the picture. We don't know that much as we know for the case of MG. But today, so what we are going to talk about mostly is about abelian varieties, Jacobians, the Torelli morphism linking to, and mostly about the tropical versions of these. I'll try to use less time to talk about the classical spaces. All right, so this is about the background, so the classical, the algebraic geometry background. So an abelian variety, let me remind you, it's just a projective variety that is endowed with a compatible group structure. So it's a projective variety with a group structure where where the operations are morphisms, and and we say that it's principally polarized if there is a class of an ample line bundle with a one-dimensional space of global sessions that we choose. So, for instance, elliptic curves are abelian varieties of dimension 1. And then if you want to think of abelian varieties of higher dimensions, just think of products of elliptic curves, for instance. Now, over C, abelian varieties can be seen as complex tori. So we'll use this notation over here, CG mod out by a full dimensional lattice. And the principal polarization can be given by a suitable integral definite positive G times G Hermitian matrix H. So in particular, if we have a smooth algebraic curve of genus G, we can define the Jacobian of C to be, so the Jacobian of C is indeed an abelian variety of dimension G, which comes with a principal polarization, which is given by the theta divisor. And again, if we think of C, we can think of the Jacobian as a complex torus defined like this. So the dual space of the space of sections of the differentials, mod out by the lattice of H1 with integer values. So on the other hand, we saw last time that it is important to consider nodal curves if we want to at least if we are interested in tropical interpretations, but Jacobians of nodal curves are not abelian varieties in general, so they are only semi-abelian. However, so what is going to be important in the classical story, at least, but I'm not going to enter too much into that today, is that there's a well-developed theory of compactified Jacobians, which you can see as the generated abelian varieties, and that will play the role of the boundary points that we are going to consider. Okay, so what about moduli spaces of abelian varieties? So just like for the moduli space of curves, there is a moduli space of principally polarized abelian varieties of fixed dimension, and this is usually denoted by IG. And again, this is a coarse moduli space for a moduli stack that we usually denote with the calligraphic letters, which parameterizes principally polarized abelian varieties of this dimension G. This is a smooth moduli stack of dimension G plus 1 choose 2, but it is not proper. And there is a theory of toroidal compactifications due to Ash, Mumford, Rappaport-Tai in the 70s with the aim of providing compactifications of this moduli space. So in order to provide compactifications for this moduli space, we have to choose a combinatorial so this is going to depend on combinatorial data sigma, which is going to be well defined soon. So there is not one single compactification of AG that we will consider. So there is a compactification for each of these data sigma that is going to be defined in some minutes. So finally, these compactifications are called toroidal, so toroidal compactifications of AG, and they define the linear Mumford moduli stacks, which compactify the moduli stack of abelian varieties. But there is a big issue here, which so remember, in the case of curves, I insisted in the fact that the moduli space of stable curves was a modular compactification, meaning that we were adding points in the boundary and we were able to give an algebra geometric interpretation for these points in the boundary. So unfortunately, this is not the case in general for boundary points in the toroidal compactifications of AG. So this is something that makes our life harder when we want to study these compactifications. But well, there's going to be a modular description in one situation. I'll mention that later. Okay, so this is the picture with the Torelli map that is this includes everything, every character that I want to see, of which I want to see a tropical version today. So we talked a lot last time about MG, and so the moduli space of smooth curves of genus G, it's compactification via stable curves. So how is this going to be linked with the spaces we just introduced? So the moduli space of abelian varieties of fixed dimension G, and the compactification, and one compactification AG sigma. So what's the idea? So there's a classical morphism between MG and AG, which is called the Torelli map, or the Torelli morphism. So how does this work? So given a curve C, the Torelli map TG sends C into the Jacobian of C with the principal polarization given by the theta divisor. So it's just the natural thing that one could expect. So the Torelli theorem states that this map is injective. So this is why I use this arrow here. So in the fact that we have MG injectively mapping inside AG, as you can imagine, is really a big advantage to study MG itself inside the moduli space AG. You can bring properties of curves inside abelian varieties, and you can go back and forward as you wish. It's really a very useful and important map in algebraic geometry. So of course, it's interesting to understand if this map can be completed, can be extended in the compactifications. So this is the dashed arrow I have here. So we already know about MG bar, and the idea is, can we extend the Torelli morphism in MG bar? So a problem is that, as I mentioned before, the Jacobian of a nodal curve is not in general, so it's not an abelian variety in general. So what makes sense, as I said, is that we consider TG bar, so the extension of the Torelli map in MG bar, by considering a suitable compactification of the Jacobian. So there is a very developed theory of compactifications of Jacobians. There's a whole variety of possibilities that we can choose. And there is a choice that one can make such that the compactification of the Jacobian that we take is particular, sits inside certain compactifications of the moduli space of abelian varieties. So the point here is, we take, is it possible to take a suitable compactification of the Jacobian together with a principal polarization or some version of these, such that not tropical yet, such that the Torelli map extends from mg bar to a compactification of the moduli space of Abelian varieties. So as I said, having this map and the properties of this map in classical geometry really is a very, very fruitful tool that we have to study both curves and Abelian varieties. So of course, it's interesting to understand if this is the case. So as we'll see, this is going to be possible for two different choices of this combinatorial data that we can choose in order to get compactifications of AG. So this is possible. So far we know that this is possible for the second Voronoi decomposition and for the perfect cone decomposition, which are two different decompositions of a certain cone that I will define soon. So the aim of today's talk is to study the geometry of the compactifications using combinatorial methods and give tropical interpretations for the boundary points as I mentioned in the keywords. So the idea is to give a tropical version of the downstairs of the arrow of the map down here. And so we already gave a tropical interpretation for the left-hand side. So the idea is give a tropical interpretation for the right-hand side and for the map, and make sense of the map. So it will make sense if, so we saw that MG trop is constructed in the category of cone complexes or generalized cone complexes. So the idea would be that we can also have a tropical version for AG in the category of generalized cone complexes, and ideally the map we want to define would be a map of generalized cone complexes. All right. So here, this is the combinatorial data sigma that I talked before. So the combinatorial data that we have to give in order to have a compactification of AG. So it starts like this. So the main character for us for the rest of the talk is going to be omega G. So this is the cone of positive definite quadratic forms on RG. So we are going to see this, we're going to see a quadratic form as a symmetric matrix. So this is, so we're gonna see the cone inside R to G plus 1 choose 2. And since we want to deal with tropical versions, we have to choose a compactification of these. So the important thing here is going to be omega G rational here. So it's a partial compactification of omega G inside omega G bar. So this is the cone of positive semi-definite quadratic forms on RG whose null space is defined over the rationals. So omega G rational, which we will use a lot until the end of the talk, is again obtained in the closure of omega G, the cone of positive definite quadratic forms. So this is going, so the elements in our space are going to be positive semi-definite quadratic forms with null space defined over the rationals. So this is our space. So this is where we are going to work today. So over this cone, we can act via the group GLGZ, acting via the usual law, HQ equals to HQ H transposed. And so now we are all set to define the admissible decompositions, which are the combinatorial data that we have to define. So an admissible decomposition.
We have a question: null space is the set of null vectors or the kernel?
Sorry, so it's the kernel, yeah. The admissible decomposition of an admissible decomposition of this of our omega G rational is a collection of rational polyhedral cones sigma mu So these are rational polyhedral cones inside our space, which satisfy these axioms. So the first is that if we have a cone in our collection, then a face of the cone is still an element in the collection. Then the intersection of two cones is a face of both cones. And third condition is that if we have a cone inside the collection and an element in the group, then if we act via this element, we're going to find again an element, a cone in the collection. And this is a very, very important condition. The set of cones inside the collection mod out the action of the group GLGZ must be finite. So the number of cones up to the action of the group must be finite. And then the last condition just says that we want the cones to cover the whole space. Okay, so there's another question. Okay, so as I said, so this is the combinatorial data that allows us to define that is used also to define the toroidal compactifications of AG, and we'll use them as well to define tropical abelian varieties. So this is the definition, the original definition of tropical abelian varieties due to Mikhalkin and Zharkov. So a principally polarized tropical abelian variety is a pair A given by a real torus of dimension G, which you just identify as being Rg divided by Z to the G, and quadratic and the quadratic form Q in our space omega G rational. And we say that A is pure if the form is positive definite, meaning that Q is in the cone of positive definite quadratic forms of rank G. So we say that two tropical varieties are isomorphic if the quadratic forms so if the quadratic form of one is sent to the quadratic form of the other via the action of the group GLGZ. So meaning that the two quadratic forms that define our two tropical abelian varieties are in the same orbit of the action of GLGZ. Okay, so as a space, the moduli space of tropical abelian varieties of dimension G up to isomorphism is just going to be in correspondence with our cone omega G rational divided by the action of GLGZ. And we will just denote by IG tropical pure with the P here to define pure tropical abelian varieties of dimension G up to isomorphism. So this notion of isomorphism again. This is just in bijective correspondence, as I said, with the quotient of the cone of positive definite quadratic forms by the action of GLGZ. All right, so this is our definition of the set of tropical abelian varieties of dimension G. So the reason I think for defining them like this is just that it's analogous to the situation of complex abelian varieties in the classical situation. So this is, I think, the maybe one reason why one can think of defining A like this. Of course, now we want to give these sets a structure, which hopefully would be the structure of a generalized cone complex. And the cone complex structure of AG tropical that we will give will depend on the specification of an admissible decomposition of omega G rational in the sense that we just defined. So again, so we define AG tropical as sets as this quotient. So the set of all positive semi-definite quadratic forms with rational null space. and mod out by the action of GLGZ. And so this is just as a set. In order to give this set a structure of generalized cone complex, again, what we have to specify is a decomposition of an admissible decomposition of the cone omega G rational. So today we're going to see two such decompositions. So the perfect cone decomposition, which we're going to denote with the sigma p, and the second Voronoi decomposition, which we will denote with sigma v. And the reason why we want to see these two decompositions is that, again, these are the two decompositions for which the classical Torelli map will extend to the moduli space of compactified abelian varieties. Okay, so let me, before telling you about sigma p and sigma v, I want to tell you that indeed, using such decompositions, we can endow the quotient of omega G rational by the action of GLGZ with the structure of a generalized cone complex. So given an admissible decomposition sigma of omega G rational, we can endow the quotient of omega G rational by this action with the structure of a generalized cone complex, where the cells are going to be the quotient of the cones in the collection divided by the action of GLGZ. So this was proved in joint work with Melo and Filippo Viviani. So we have a different, we call them different, we call the structure differently at our work. We call it Schottky fun, but actually it's just a matter of translation. So it really, so the idea is that such a decomposition will allow us to define, so it's not a topological quotient, the one that we want, it's what we call there a stratified quotient, and this stratified quotient will satisfy the same conditions that we need in order for this to be a generalized cone complex. And again, so for terminology, when I refer to AG tropical with a sigma, I mean the moduli space of abelian varieties of dimension G associated to sigma, meaning that the generalized cone complex structure is the one associated to the quotient with these cells. All right, so I take the cones again, the cones that define the decomposition. Remember, so this is a collection of cones dividing omega G rational, and there's this action. We mod out by this action, and there's a way to take a representative for each class and to build afterwards a space out of this, which will have this structure. And if I put the B here, I'll just mean the locus inside AG tropical sigma of pure tropical abelian varieties. All right, so
there's a question in the chat.
Yeah.
There was a single point of MG trop corresponding to smooth curves. Is there a single point of A trop PG corresponding to Jacobians of smooth curves?
Yes. This is going to be clear in a minute. Yes. This is going to be the case. Yes. So this is going to correspond to the vertex of our cone. Yeah. Okay. So this is about. So now I'm going to define the two decompositions of the cone omega G rational. So the first one is called the perfect cone, or first Voronoi decomposition. You might have already seen this. Otherwise, it could maybe seem a bit technical, but it's just a definition. So how do we define this decomposition? So the idea is which are the cones. So I have to tell you which are the cones that we consider in order to decompose our omega G rational. And then it's a theorem due to Voronoi in both situations that these cones do form an admissible decomposition, meaning that they satisfy the conditions I introduced in the beginning. So here it is. So take Q in omega G. So this is in the cone of positive definite quadratic forms. And consider this set. So it's a set of integer vectors such that the quadratic form attains its minimum among its values in other integral elements, integral vectors. And then for each element in this set, consider the rank 1 quadratic form given by multiplying C with C transposed. This is an element in omega G rational. And then we can define sigma Q to be the rational polyhedral subcone of omega G rational, which is given by the convex hull of the rank 1 forms that we obtain from elements in MQ, meaning, so we take all C's in this set, we consider the associated quadratic form obtained by multiplying C with C transposed, and then we take the convex hull of all of these. This is a polyhedral, a rational polyhedral cone in omega G rational. And the theorem, as I said, due to Voronoi in the beginning of the last century, says that indeed, if we do such a decomposition of omega G rational, we do get an admissible decomposition in the sense that I defined earlier. And this is known as the perfect cone or first Voronoi decomposition. So we will use the notation sigma p for this decomposition. So just a curiosity, the quadratic forms Q such that sigma Q has maximal dimension, which is G plus 1 choose 2, are called perfect, and that's why we call this decomposition perfect cone decomposition. All right. Yes, so this is the example in dimension 2. So remember, now we are talking about dimension. It's not genus. So genus is going to be in some minutes back when we talk about Jacobians. So if you take G equal 2, you can show that the unique cones in sigma p up to GL to Z action are these ones. So here we define the quadratic forms using the matrices. So there's the cone associated to this matrix, the cone associated to this matrix, the cone associated to this matrix, and the one associated to this matrix. And here you see all matrices that lie in the same orbit of the action of GL to Z. So in the exercise sessions tomorrow, it's maybe we can check these things directly. So yeah, if you're curious to see how can one prove these things, maybe you could come. Okay, so this is the example for G equal 2 for the perfect cone decomposition. So the second decomposition that I mentioned before is the second Voronoi decomposition. So how is this set? So maybe you know about the lone subdivisions, and so this is the decomposition associated to the lone subdivisions of RG. So let's define it carefully. Maybe you didn't see it yet. So take this time Q to be a quadratic form in omega G rational, and consider this map. So it's a map from ZG to ZG times R. So we can see this inside R to the G plus 1. And this map sends X, an element, a vector X in ZG, to X, comma, QX, meaning the quadratic form associated to X. And now we consider the convex hull of the image. This will be inside R to the G plus 1. And the lower faces, and if we project the lower faces of this convex hull back to RG, then this will give an infinite ZG periodic polyhedral subdivision of RG. and which is called the de Leon subdivision of associated to the quadratic form Q, and that we denote with del Q. So the de Leon subdivision of Rg associated to the quadratic form Q. And now we can define cones associated to each de Leon subdivision. So given the Leon subdivision D, we denote with sigma D the set of quadratic forms in omega G rational which define the same de Leon subdivision of Rg as D. And if we close it up inside omega G rational, then we have a well-defined rational polyhedral cone, which is called the secondary cone of D. And again, Voronoi showed that this collection of cones, sigma V, is going to define an admissible decomposition of Rg. So this is called the second Voronoi decomposition of Rg, of omega G rational, sorry. Okay, so again, there's a curiosity here about the maximal, about the maximal.
Another question.
Yes.
Are these cone decompositions the same used in non-tropical settings? Used to construct toroidal compactifications of Ag?
Yeah. Yes, they are. Yeah. Okay, so the maximal dimensional cones are those of the form sigma D, where D is a triangulation, meaning that D consists only of simplices. All right. So again, we have the example in dimension 2. So these are the possible de Leon decompositions. Maybe the person who asked the question will recognize these pictures. So these are the de Leon decompositions of the possible de Leon decompositions of R2. So we have 4 of them, and these are associated to the cones in omega 2 rational. And as if you remember, it's exactly for G equal 2, they actually coincide. So the cones of sigma V and of sigma P are exactly the same in dimension 2. All right, so again, if you've never done this, maybe it's interesting to figure out how to obtain these decompositions. If you start with some of these quadratic forms, maybe it's possible to be computed. All right. So now let me tell you some classical results about these 2 decompositions. So to justify why they are important in classical classical algebraic geometry. So the note, as I said in the beginning, the admissible decomposition, the compositions of omega G rational are the combinatorial data that is necessary to define a toroidal compactification of Ag. So this is not Ag tropical now, so Ag classical. So using both the perfect cone and the Voronoi, the second Voronoi decomposition, we can define toroidal compactifications of Ag, which we will denote with Ag bar P and Ag bar V. So these are the perfect cone and second Voronoi toroidal compactifications of Ag corresponding to these decompositions. So they are important, and so Ag. So the compactification associated to the perfect cone decomposition is due to work of Shepard-Barr in 2006, shown to be the canonical model of Ag for G at least 12. So this is the canonical model in the sense of birational geometry. And Alexiev in 2001 showed that the second Voronoi decomposition showed that the compactification of Ag associated to the second Voronoi decomposition is actually, well, at least is the normalization of a compactification of AG, which has a modular description. So this was quite quite an important fact. So because it was not known if some of the toroidal compactifications would admit or not a modular description. So Alexeyev constructed in 2001 a compactification, which is of AG, which parameterizes what he calls stable semi-abelic pairs. And this compactification has several irreducible components, but the main irreducible component, which is the one which contains AG in its interior, this irreducible component might not be normal, but its normalization is the second Voronoi compactification of AG. So the compactification of AG associated to the decomposition of omega G rational that we just saw. So due to the second Voronoi. So, and from the point of view of this talk, which is we want to extend the Torelli morphism from Mg to Ag, these are the only two decompositions that make sense to consider, since we know now that in both situations, so both for Ag bar V and for Ag bar P, the Torelli morphism does extend from as a regular morphism from Mg bar to Ag bar, either V or P. So for the second Voronoi decomposition, this was well known already to Mumford and Namikawa. But for the perfect cone decomposition, this was shown much later by Alexeyev and Bruniate in 2012. So what happens here is that we take so given a curve, a stable curve in Mg bar, we take its compactified Jacobian in degree G minus 1. Well, a certain compactification of the Jacobian in degree G minus 1, and they show that it's possible then to extend the Torelli map to these two compactifications of Ag as regular morphisms. And again, using the fact that that the second Voronoi compactification has a modular description, Alexeyev showed that that this extension of the Torelli morphism admits also the Torelli morphisms admits a modular interpretation, and this was used to describe its fibers. So remember, in the beginning we said that the Torelli morphism, so the classical Torelli morphism, is injective, and this is really a very important property, because we can see Mg inside Ag, and we talk about the Jacobian locus, and the fact that it's injective is really helpful. So for the compactification, it's clear that it could not be injective. It will be clear for us in a moment. But so of course it's interesting to understand if you can extend which kind of curves, which kind of nodal curves might have the same image in Ag bar V or Ag bar P. So actually the morphism is defined in the same way for both compactifications. So the sentence here so the point here I should make is that the Torelli morphism is defined in the same way, but what happens is that in the image of, so in the locus containing the image of the Torelli, both these compactifications coincide. So I will say more about this in the end. All right, so so let's talk about tropical Jacobian varieties. So this should be special types of tropical abelian varieties. So this should be real cones together with a quadratic form. So how does this work in the case of a tropical curve? So consider a tropical curve. I'm using the notation here gamma WL. So this is the graph together with the weight and the length for the edges, remember from Monday's talk. So how do we define a real cone out of this data? So what we can do, so this was also defined by Mikhalkin-Jarkov in the case of pure tropical curves, and this is just an extension of their definition to the case where you could also have weights. So the Jacobian of such a tropical curve is defined to be this torus, so it's H1 of the graph with values in R, summed with R to the power of the total sum of the weights, and then divided by the same things but with integer values. So divided by H1 with of the curve of the graph with values in Z plus Z to the total sum of the weights. So exercise show, this is an easy exercise, show that this is dimension G real torus if the genus of C is G. So show if you're annoyed with the talk, show that if you have a tropical curve with genus G, that this is a real torus of dimension G. So this is the real torus of dimension G, and the quadratic form is defined like this. So it's trivial on this extension to the weights. Okay, so you see that if you have your curve to be pure, remember this means that there are no weights. So if there are no weights, this is not here. And in this situation, you would have a positive definite quadratic form, so a pure tropical abelian variety. Otherwise, you will get zero. So there was someone asking about the cell in the moduli space of tropical curves corresponding to smooth curves being only a vertex. So in this situation, you see what you get as a Jacobian, as a tropical Jacobian, is that here you get nothing. It's the opposite situation, right? So here you get nothing, and you get only, so R to the power of G divided by Z to the power of G, but you get a trivial quadratic form. So which is actually the data that you're interested in order to define your Jacobian. So, so as I said, so in the part of the weights, it's just trivial. And in the part corresponding to the cycles in your curve, it's defined like this. So you QL associated to the sum of so these are the edges of your graph with some coefficients. You just define it like this. It's just the sum, the coefficient squared, and then the length of the edge where you're computing things. So this is positive, and it's well defined in the H1 gamma R. So again, in the exercise session tomorrow.
Another question: is the choice of the lattice Z to the W and R to the W canonical at this point?
Well, you can choose that, because then you can change the quadratic form. So if you say that you are choosing one, once you choose one basis for your lattice, then for your H1, then since the quadratic form is well defined up to the action of GLGZ, you can identify yourself safely with R to the G mod Z to the G. So it's a choice that you can make. All right. So again, in the exercise session tomorrow, I think it's going to be possible to compute this example over here. So these are all Jacobians. So these are all dual graphs of tropical curves of genus 2, I think, that was computed in the exercise session yesterday. So C So, yeah, so this is weight 1. So there's another question.
There's a follow-up question. Can you use this technique to interpret a principally polarized tropical abelian variety of dimension G as a tropical abelian variety of dimension G plus n?
Oh, you mean the points?
I'm not sure. Felix, you want to elaborate?
Yeah, sorry. So my question is, can you use this technique of just like adding more real dimensions and choosing an arbitrary lattice like set in R to interpret a tropical abelian variety of any given dimension G as an abelian variety of higher dimension, like any G plus a positive integer?
I see. Tropical, you mean? I think yes. I think tropical. The answer tropically. I think the answer is yes. Yeah, you just add up some trivial torus with a trivial valued quadratic form. I think this is yeah. I think the answer is yes. If I understood correctly, yes.
Okay, thank you.
Yeah. Okay. So. So yeah, back to the example here. So these are all curves of genus 2, and it's not hard to compute. So it's not hard to compute their Jacobians. So what you have to do is you choose an orientation for your curve, and so that you can choose a basis for the H1 for the space of cycles in your curve, and then you compute using this rule the values of the quadratic forms in the basis, and you see that you get these matrices. So as you see here, so these two curves have the same quadratic form, and also these two curves have the same quadratic form, and so means that so this is this means that the tropical Torelli morphism will never be injective. So what you don't see in the Torelli morphism, this separating edge, and you don't see you don't see separating edges. I think this is the only thing that we can see here. There are other things that you don't see. I will make a precise statement in a minute. Okay, but so in the exercises tomorrow, we can, so it's easy to convince ourselves that this is always the case, that if you have a separating edge, for instance, that that if you contract your separating edge, the Jacobian will not change. The tropical Jacobian doesn't change. And there's a classical version for this, actually. Yes. So if you have a separating node in a nodal curve, which corresponds to the separating edge in the tropical sense, so the Jacobian doesn't see this as well in the classical picture. All right. Oh, now I have to do something here in order to be able, yes. Okay, so this is the statement of the Torelli, the tropical Torelli map. So this was shown together with Silvio Branetti and Filippo Viviani like 10 years ago or something. So it says the following. So the Torelli, the tropical Torelli morphism is just what, it's just the only thing that you could have is take a curve in MG trop and send it to its Jacobian. So this is, as we saw, this is a tropical abelian variety. The point is, will this be a morphism of generalized cone complexes? Meaning, so here you have this, you have a decomposition of this. So this space is obtained as a generalized cone complex with cells that you glue together accordingly to the structure of this category that I defined last time, the SG. So the category of stable graphs with the contractions. And for this, it's the same thing. So you have a decomposition of your omega G rational according to these cones that are in the collection of the admissible decomposition that you choose, and you consider the quotients of these cones. These are the cells. So the cells are cones up to the action of GLGZ. And the statement I'm making here is that a cone of that is a cell in MG tropical consisting of curves of the same combinatorial type will land inside a cone of the decomposition of omega G rational up to the action of GLGZ. So cells are sent into cells. So this is the most important thing that you have to show in order to state this here. So this is the case for both the perfect cone and for the second Voronoi decomposition. So in particular, this map is continuous, where the topology is the topology of generalized cone complex that I defined last time for MG tropical, and the one associated to the decomposition sigma that you are prescribing in each situation. It maps cells into cells, preserving its integral structure is part of the statement. And moreover, there is something more that we have in this situation, which is the mappa is full, meaning that cells are sent surjectively into cells in both situations. Okay, so in the beginning as well, I mentioned that one could try to understand a version of the tropical Torelli morphism. Means
a question: yes. Is the surjectivity between cells over Z or over R?
I think it must be both, because so the cells must preserve the integral structure, and they are surjectively into R. So yeah, I think the integral part always go to the integral part as well. So it's part of the requirements. So I think the answer is yes. All right. So so the tropical Torelli theorem was proved by Lucia Caporaso and Filippo Viviani. And says that two tropical curves have the same image. So the image of two tropical curves via this morphism are the same if and only if, so if and only if one can be, so let me say this in words, and then I will explain. If the three-edge connectivization of one curve is in the same class as the three-edge connectivization of the other curve. So in particular, if you are in the locus of free vertex connected curves, then this doesn't do nothing. So meaning that this the tropical Torelli morphism is injective in this locus. Whereas if you are in a locus where your curves are not three vertex connected, then as in the situation I showed before where you have separating edges, for instance, then the tropical Torelli could identify different curves. And when will curves be identified via the Torelli? So if one is sent to the other via two types of operations, one is that you can contract separating edges, and the other one is that you can contract pairs of edges such that that are in the same C1 set. The C1 set is a set so says that each circuit in your curve passing through an edge should pass into the other edge. Well,
question: three vertex connected.
What's three vertex connected? That's the question.
Yes.
Okay, so three vertex connected. So it's so I'm thinking about the graphs. So these are tropical curves. So they are graphs with lengths, and it's three vertex connected if your graph is three vertex connected, meaning that in order to separate your graph, you have to remove at least three vertices. This is a possible definition. Okay. So now, in order to, I want to end with a version of the Schottky, theorem. So the tropical Torelli, so the Torelli map classically is associated to two important types of theorems. So the Torelli theorem, which states that the Torelli map is injective. And then there's a second type of problem, which is characterizing the image of the Torelli map, meaning inside AG, can you give a characterization of the image of the Jacobian loci? And so in order to give a tropical version for this, I have to talk briefly about matroids. So let me remind you that a real matrix is said to be totally unimodular if each square submatrix of it is as determined -1, 0, or 1. And it's unimodular if there is a matrix in GLGZ such that HA is totally unimodular. And we say that it's simple if it does not have 0 columns or proportional columns. And we say that two unimodular matrices are equivalent if one is sent to the other via this relation here. So the importance of unimodular matrices for us is that unimodular simple matrices up to this equivalent relation here are in one-to-one correspondence with regular simple matroids of rank at least G, meaning that you associate to the matrix the vector matroid associated to the unimodular matrix, which is going to be a regular matroid. Okay, so then, given unimodular matrices, you can define rational polyhedral cones in omega G rational in a similar way as we already saw in the talk. So given a simple unimodular matrix, you can define this cone, sigma A, to be defined by, so it's generated by the quadratic forms obtained by multiplying V1, V1 transpose, etc. So these are the vectors, the column vectors of the matrix. And then you define the metroidal subcone inside omega G rational to be the union of these cones. This is contained inside omega G rational, and it's called the metroidal locus inside omega G rational. All right, so so it's a statement that the collection of these cones yields an admissible decomposition of the metroidal locus inside omega G rational, meaning that inside omega G metroidal, this is an admissible decomposition, meaning that it satisfies the conditions I said in the beginning. And now, together with Filippo Viviani, we proved that a statement that maybe, so in the beginning I said something about it, that the cone belongs to both the perfect cone and the second Voronoi decomposition if and only if it belongs to the metroidal locus. So the intersection of the collection of cones inside the second Voronoi decomposition and the perfect cone decomposition is this metroidal locus. It's a very interesting locus where I think there are lots of things to be understood inside this locus. So maybe sometimes it's hard to understand the whole decomposition, but still the metroidal locus is more feasible, and it's it's a good place, for instance, to check the Jacobian locus. So here is a sketch of the proof, which I will not go into, but at least if you're curious, then you can check the slides to have an idea of how can one show this statement. And well, so this is because now I can state a tropical Schottky theorem. So this was again in the same paper together with Silvia Branetti and Filippo Viviani. So we showed that if you consider a cell inside the moduli space of tropical curves, meaning so for each combinatorial type of a tropical curve of genus G, you consider the image of via the Torelli map, and the image of this cell is the cone associated to to the simplification of the cographic matroid associated to gamma. So gamma is a graph. It has a cographic matroid. It's a regular matroid, so that's in the sense, so sigma of this regular matroid is in the sense that I defined before. So it's associated to any matrix that defines the regular matroid M star gamma. So it's this is a statement which in particular allows us to conclude that the image of the tropical Torelli map is this locus that we call AG cographic, which corresponds to the image of all these cones. And so the image has pure dimension 3G minus 3, and the generic point is of the form Jacobian of C for C, such that the graph is associated to a 3 regular and 3 edge connected graph. And we could show also using these combinatorics that the tropical Torelli morphism has tropical degree 1, which was something that Mikhalkin and Zarkov conjectured to be true in their original work. Okay, so just before I finish, let me just show a list of references, which was something that someone asked last time. So here it is. So I have this list of references in the last slide of the second lecture. Okay, so thank you very much for your attention.